All right, I think we can get started, and people may still enter the room. I know if you don't know this building, it's sometimes hard to find your way around and find this room. Anyway, so welcome. Welcome to this course, Concepts of Multilevel, Longitudinal and Mixed Models, and I will first start with giving you a little bit of background, introduction, general context of this course, and then we will gently start to get into the examples and the applications. And I will explain you also a little bit of what is the aim of this course, because the title says, well, first of all, my name is Geert Verbeke. If you had not guessed that, I'm Geert Verbeke. And I'm from the biostatistics unit here in the medical faculty. That's also why we are here in this building. But anyway, that also means that many of the examples that you will get to see throughout the course are taken from medical experiments, medical applications, but of course you can equally well think of other situations where you would have similar kind of data sets or data structures that would require similar methodology to analyze them. So the title of this course is Concepts of Multilevel Models, Mixed Models, Longitudinal Data Analysis. So we will not see all the technical details. So this is not a theoretical course. So it's only a general introduction to mixed models, sometimes also called multi-level models. What is longitudinal data, models for longitudinal data, and what are the small differences, sometimes subtle differences that you also see in the literature between a model for longitudinal data. People sometimes refer to repeated measurements. Then people talk about multi-level models or multi-level data. They talk about mixed models, and basically it all refers to the same thing. But it's just different terminologies. Hello, good afternoon. But we will see that gently through the course, so don't worry about that. But we will not see the mathematical details behind these models. And I know that, I mean, the group here, but also the group online, because there's also students who follow this course online, is very heterogeneous. There's people who really take that as part of the master program in statistics. And just for my information, who is from the master program in statistics? Okay, so that small group, okay. There's also other people. So some of the information that I will give is only for the people in the master program. Some of the information is then for everyone. So that makes it a little bit difficult. But so there's also people who follow this course online. You all have a different background. And why am I saying this? Well, the reason is, well, for the people, especially in the master program in statistics, if you really want to go into this kind of methodology, there is a follow-up course next year, so in the second year, first semester, which is called Longitudinal Data Analysis. And there you will see many of the examples that we discuss here. You will see them coming back with similar models, of course, but then we will really dive into all the theoretical details. How do you do inference? How do you get parameter estimates? Are there different methodologies available? What are advantages, disadvantages? So some of the questions that may come up during this course are just way too early to address them in this course, because we don't talk about the theory behind all these methods. So the aim of this class here is just for you to recognize situations in which this kind of methodology is needed, is helpful, and also give you sufficient examples that can help you to apply these techniques without making severe mistakes in a practical situation. But if you have really questions about how do I compare models, how do I calculate that particular p-value, because we will see many different test statistics, p-values, all different procedures floating around. We will not talk about all these details. That's for next year. And also some of the other questions that may come up, that will be for next year. But of course, if you have questions, don't hesitate to interrupt me or to just give me a sign. And if it's too early to address that question, I will tell you, and then I will say, come back next year, and then we will talk about that in more detail. But of course, some questions can be addressed in this course, and then we will address them in this course. So if I just, well, first of all, the notes that you see here, so copies of the slides, you can find them on Toledo, and I hope you have all been able to find them already. If not, just give me a sign, because the fact that some people are not within the master program in statistics makes it sometimes a little bit more difficult to get access to the Toledo site. If that's the case, just let me know. But these are the notes, or these are just copies of the slides. And some of the other material I will discuss later on, which is also on Toledo. But if you just look at the content table of this course, well, first of all, we will start with a general introduction. That's for today. Then we will start looking into some of the first examples. But what you will always see is that each data set basically starts from like a practical application. It's almost always a particular data set with a particular structure, with a particular research question, and then we will start thinking about what is now particular about that data set, how can we turn that into a statistical model. We will write down that model so that we understand what all these parameters in these models really mean, and then we will apply that in software, and I will come back to the software part a little bit later today. So we will apply it in software, we will interpret the results that we get, outputs from analysis, so that we really understand what we are doing, why we are doing that, and how to interpret all these results. And that's basically the most important thing for this course, so that you, by having seen many examples, that you can recognize situations where mixed models are very useful, and that you can apply them without making severe mistakes, because there's many mistakes you can make if you start to use mixed models. Now, this part 2 here says linear mixed models, and that means the context will be a little bit similar as what you know from linear regression or analysis of variance. So we will typically have a continuous outcome that we will have to analyze. That's a big part here. If you look at the number of pages, it goes all the way to like page 178, so that's a big part of this course. And that's not because this is the most important part, but it's because this is, of course, the part where many of the aspects related to mixed models will be discussed for the first time. And then you need a little bit more time to explain that in detail. If you see it again in the next example or in a third example, then you do not need so much time to repeat that all the time, and that's why the later parts take a little bit less space also in the notes. Then we will go to generalized linear mixed models, and these are situations where we typically have a discrete outcome, like a binary outcome or a count outcome. These are like the most frequently observed examples in practice. And also there, we will see, always, we will start from a practical application and look at that particular application and try to solve that problem. And then finally, and we will see how far we can get in this part, we will also say something about nonlinear mixed models, nonlinear models, because there's a number of situations in practice where you really need these models, but you will see by the time that we will get to this part, there will be no new methodology, basically, because we have discussed that all in the previous chapters. It's just different kinds of models, different kinds of applications that we will see here. So that's a little bit an overview of what you can expect in this course. And as I said, if you have questions, don't wait until the break. Of course, we will have a break because we have long sessions. 3 hours, that would be too long, so about halfway we will keep a break. But don't wait until the break or until after the class to ask questions. Just interrupt me. Okay. Okay. Maybe a few related references. I will not discuss them all in detail, but this is just a whole list of textbooks, basically. Good afternoon. No problem. I know it's difficult to find. Yes. All textbooks that are somewhat related to this course. I'm not going to discuss them all at once, but if you would look for additional information, or you would want to apply it in a more specific context other than what we have seen here, and you're looking for a textbook, just talk to me, and I can point you to related textbooks. There's two books that I'm going to focus on in a little bit more detail, and these are these two, which are by myself and my colleague here at Molenberg, which is on linear mixed models, and then models also for discrete longitudinal data. And why do I want to list them here in particular? It's because basically almost all the examples that we will discuss have been taken from these books. So if you want to read more about this, look first in those books, because there you will recognize the same examples. You will see the same notation, so because different textbooks sometimes use different notation, so to make it easier and to find a book that is more related to how we introduce the material here in this course, then look in those books, because then you will more easily find your way. Now, these books will also be used next year for the longitudinal data analysis course, for the ones who take that class. Of course, needless to say that these books contain much, much more information than what you need for this course here. So don't think that I'm expecting you to read those two books from the first page to the last page, because that's just going to be impossible. These books contain much more material than what is needed for this course. I already referred to the fact that we will see many examples, and we work them out with software in the course notes here, and then we will look at these outputs and interpret these outputs and these results. And there's many software packages around nowadays. In this course, we will focus on SAS. I'm not saying you have to use SAS, because if you're more familiar with other packages for your assignment, for those who need to take the exam, I will come back to that, you can use any software package as long as it does the right job, okay? But the reason why we focus here on SAS is, well, there's many reasons. First of all, students in the track biometrics often end up in the pharmaceutical industry, and then it's important that you're familiar with SAS, because the pharmaceutical industry is full of SAS. That's really the gold standards, and so that's to get you already introduced in SAS. SAS is, of course, one of the major statistical packages, and I know there's also others. But then more particular for this course, an additional very important reason to use SAS is that it's just the best. And for linear mixed models, so the whole first, let's say part 2 in our course notes, all these packages basically do more or less the same. It's just that SAS has many more additional options, tools, is much more flexible on if you have a model that does not really fit within the standard class of models, you can tweak it very easily in SAS to get it in. But if you can fit the model in R or in SPSS or in SAS or in whatever package, you will always get the same results. So that's not the issue. The big issue is generalized linear mixed models or nonlinear mixed models. So SAS has 3 different procedures: proc mixed for the linear models, proc mixed for the generalized linear mixed models, proc NL mixed for the nonlinear mixed models. So this corresponds to these 3 parts that I showed you in the contents table. When you go to GLIMMIX, so generalized linear mixed models and nonlinear mixed models, it turns out that writing down the model is not so difficult. What is difficult is getting estimates for the parameters in that model. Because, many of you know how we traditionally get estimates in the statistical context. We do maximum likelihood estimation. Good afternoon. Well, many more people. I know, so don't worry. But now you know for next time. If you can find it back, yes. Let's see. Very often we use maximum likelihood estimation. So, and to do maximum likelihood, basically what you need to do is you write down your likelihood and you maximize that likelihood with respect to all the parameters in that function, unknown parameters in that function. But it turns out that these likelihoods, you can quite easily write them down, but they're full of integrals. Integrals that can no longer be analytically solved. And that's the whole problem. Because if you remember from other classes, a likelihood is typically like a product over independent observations. And if each term in that product contains an integral, and you have like, let's say, a few hundreds of observations, that would mean a few hundreds of integrals in that function, and none of these integrals can be solved analytically, then how do you start maximizing that function? And that's the whole issue. And because of that, we need to use approximations. And if you look in the literature, and we're not going to discuss that this year, but next year we will discuss that in a little bit more detail. But if you look in the statistical literature, there's many different approximations that people have proposed. And they all do something different, and they all, and that's the problem, they all lead to different results. Now, as a statistician, I don't feel very certain about using an approximation, knowing that if I would have chosen a different approximation, I would end up with different results and different conclusions. Or at least knowing that there is the risk that I would end up with different conclusions. So what you then typically want to do as a statistician is you try out several of these approximations. And if you would see that all these approximations, yes, they give you small differences in the results, but eventually you end up with the same conclusion, then you feel more safe to report that these are your final results. And there is the problem, because most of the software packages have implemented only one, sometimes two of these approximations. So if you want to try out 5 or 6 different approximations, you're stuck, unless you take the effort to always move from one package to another package. Well, you don't have that problem with SAS, because SAS has them all implemented. And the only thing you need to do in SAS is change one small option in your code. And just switch to another option, and you have another approximation. So you don't have to transform your data to another format. You don't have to write down a syntax in another program language. You just stick within the same environment. All you do is you change one small option, and you can do all these approximations and compare the results. Once again, that's not really very relevant for this year, but it will be very relevant if you go on also next for next year, but also even for this year. I mean, if you're stuck, if you do some of these analyses in R, especially like the CLIMIX, the generalized linear mixed model, R has only one approximation implemented. If you really want to be sure about your final results, then it gets tricky. So that is the reason why we focus so much on SAS. So once again, I'm not forcing you to use SAS, but all the examples that you will see here in this course are done with SAS. You will see the syntax. I will briefly explain how the syntax looks like, why it looks that way, what you do with the different options, what they mean, what they imply for your models, and then we also look at some of the the outputs that we obtain. And the outputs from all these software packages basically look the same, so that's not the issue. Also, for my information, who is familiar with SAS? Okay, not everyone, but still a good number of people. Another reason is, apart from these approximations, is that it's just most up to date with the literature. I mean, just the fact that you have 3 different procedures to fit a mixed model, that just shows that with every new release, there's new options available. They just follow very closely what is in the literature. And I did not point to that in a lot of detail, but if you look at these textbooks, then you will see that many of these textbooks are relatively recent. And you might say, well, 97, that's not all that recent. If you just look at this in comparison to the whole history of statistics, that this is brand new, okay? And of course, first the methodology is there, and the software is always like 10 years after that. So because they need to implement that. So that's why it's important that you have a software package that is up to date, that follows closely what is available in the literature and does the right things. Because this is a huge domain within statistics, and I will also explain you why it's so huge. It's a huge domain within statistics, and it's still evolving. So there's still many people doing research on mixed models or related to mixed models. Okay. We're also, yes?
So I'm convinced that SAS is the best. I'm just getting to know Bruce a little bit.
Oh, yes. Yeah.
I was wondering if I can transfer this information then to Empress if I want.
If you know, yes. If you know what model you want to, the first thing is always to very carefully think about the model you want to fit, and make sure that your model incorporates all the different aspects of your data structure, because we will have hierarchical data structures, and it's important that all the various levels of your data structure are incorporated in your model, and that you understand what that model is doing, what you assume, and what you do not assume. Once you've written down that model, and you then know how to implement that in whatever software package, and Plus is also a very flexible one, and it's also one of the better ones, if you don't talk about, but it's less frequently used, and that's why we don't use it here in this course, but it's also one of the better ones. So you will definitely be able to also fit these models in M+. That's no problem, yeah. All right. We're also asked to always say something in the first class about the evaluation. And I already stressed, I think, that this is an applied course, so it makes no sense to have a theoretical exam. So the exam will be a data analysis. So you will get a data analysis soon, maybe not next week, but then definitely the week afterwards. A data analysis, and you can start working on that analysis. So you will have a data set with a specific structure, with a specific context, and then a number of research questions that will be asked that will guide you through a number of the analyses that basically cover the entire course. You will work on that in teams. So you can already, and it's up to you to form teams, and you can do that with the people present here, but also the people who take the course online. And if there's no way to find each other very easily, tools will be made available. I will explain it once the assignment becomes available, because I will also explain it here during the course. But you can already start to think about who you would want to work with in your team. You look for teams of 4, 5, or 6 people. So between 4 and 6. 4 and 6 included. Why not less? Because then you don't have enough discussion anymore. If you only work with 2 people, you will see it's rarely black or white. It's always gray in this context. You have to make decisions, you have to make choices, and it's important that you can discuss that with your teammates. and that you can then balance out pros and contras of different techniques, and that you can choose then for that particular model. So that's why you need to have a group which is of a sufficient magnitude. Not too many, because then it's not workable anymore. It should remain feasible, of course. And what will be done is that you will then hand in the report. You can load it up for your team in Toledo, somewhere by the end of the semester, well, just soon after the semester, so it's going to be early June. But like about 2 weeks prior to the final exam. And at the exam, which is an oral exam for this course, you will only get questions about that project report that you handed in. So no other questions, no theoretical questions, because we're not going to discuss any theory, but it will be questions about why did you do this, how do you interpret that parameter, how do you get to this piece of output or to this graph, so that you can show that you've understood what you did, that you can defend yourself, and that you can argue why you did it that way. There's no unique best answer for the questions that you will get to solve on your assignment, but you need to show that you can critically think about it and that you can come with a result and with a conclusion and an answer where you have thought about it very carefully and then made a decision and then defend that decision. That's basically it. And I'm always telling students, just that you know, you don't get other questions than what is things about that report. So you need to defend your report. But of course, everything you write in that report can and will be used against you. It's just that you know that. So you need to understand very well. So don't come to the exam and say, well, I didn't do that part. It was my team member. That you need to, it's your report. You're part of the team. You need to understand. And it's up to you to discuss with your team members, why did we now do this? Why did we not do the other model? How do you interpret that result? Because that's how you learn the best, by discussing things with each other. But again, much more information about that is yet to come, but you can already start to think who you would want to work with, and if you have your team already ready, then keep that team, and then there will be a point where you can register your team. Yes?
Is this in individual or depends?
The oral is individual, yes, yes. The oral is individual. Any other questions on this? Once again, much more information will come later. Okay. This is about all the practical information. Let's now start to talk about the motivation for this course. And the first thing is, well, I've already used the terminology, but I didn't explain it. I already talked about hierarchical data. What is a hierarchical data set? Well, a hierarchical data set is the kind of data that is obtained if a sample is taken at multiple, so more than one, hierarchically ordered levels. And that's probably may look quite abstract, but let's look at some examples. Suppose you have patients. Once again, it's a medical context. Suppose you have patients, and these patients have some particular medical condition, disease or whatever, and you treat these patients, and then you ask these patients to come back next week, and the week afterwards, and the week afterwards, for every week or every 2 weeks, or maybe every week at the beginning, and then every month afterwards. And each time you take a particular outcome, you take a particular measurement. Could be anything, could be blood pressure or whatever. And just think of a very simple situation where you would have 100 patients and you would have 5 of these measurements per patient at 5 different time points. Then you have a data set with 500 observations, 5 multiplied by 100. But these data are like ordered. There's a hierarchical structure because you have your sample of patients that was taken from a population of patients, a sample of patients, and then within each patient you have 5 measurements. That's what we mean by a hierarchically ordered levels. And here there would be 2 levels. You have the level of the patients, and then you have the level of the measurements within the patients. But one is like nested within the other in this example. So that would already fit within this general definition here. The same for growth curves. If you just look at growth curves, like children that are growing, and every now and then you measure how tall they are, and you just put that on a chart, where on the x-axis you have the age of the child, and on the y-axis you have how tall they are, and then you do that for a number of children, then you also have the same kind of data because you have multiple subjects, multiple children, and within each child you have a number of measurements. So that's also a hierarchically ordered data structure. And of course, you can do that with children, but equally well with animals. You can look at plants that are growing, how fast are these plants growing, and things like that. But there's also other situations. Suppose you do a big survey in which you randomly sample a number of families in a particular region or a country or a city. That's less important, but you randomly sample families, and then you visit all these families, and you give all the family members a questionnaire. Then for every human being in your study, you have for each outcome only 1 observation. But of course, there's still a hierarchical structure in this data set, because you first have a level of the families, and then within the families, you have the family members. So you have, again, that same kind of structure in your data set. And you can already see that these clusters of observations, in the first example, these were the patients. Each patient, you had 5 observations, let's say, or with the growth curve, you would have the children, and within each child, you have a number of measurements of the growth. Here, the clusters would be the families, and within each family, you then question all the family members. You see that these clusters do not necessarily need to be all of the same size. You can have families of 2 people, you can have families of a single person, you can have families of 6 people, and even more. So clusters can have different sizes. So you can have very unbalanced data structures. Another example would be that you randomly sample 10 different towns or cities in a country, and then in each city that you have sampled, you randomly sample a number of inhabitants. Again, you have this clustered data structure, because the first level would be the level of the towns that you have sampled, and the level below that is the inhabitants living within these towns that you have also sampled. So that's what we mean by a hierarchical data structure. Or you can randomly sample a number of schools. People do that always in educational sciences. They randomly sample a number of schools, and in each school they randomly sample a number of students, and then these students are given a particular test. Well, that's also a hierarchical data structure, because you have your schools which are sampled, that's the first level, and the level below that you have the students that were then sampled within each school. Now, all these examples are examples of what we would call 2-level data structures, because we always had 2 levels. But of course, you can extend that. Just think of the following. Suppose you randomly sample 10 cities. In each city, you randomly sample 5 schools. In each school, you randomly sample 2 classes. In each class, you randomly sample 5 students, And then each student would be given the test at the beginning of the academic year and at the end of the academic year. Then you have a huge database, but it's very much clustered. Because you have the cities, within the cities you have the schools, within the schools you have the classes, within the classes you have the students, and within the students you have the two measurements at the beginning and at the end of the academic year. So this would then be called a multi-level data structure. So you can already see where the terminology comes from. If people talk about multi-level data, it's just a data structure where you have multiple of those levels. While on the previous page, these were all like two-level data structures. But that's also multi-level, because as soon as you have more than one level, it's multi-level, okay? We will first look predominantly at two-level data structures. Later on, we will also extend it, because the big step is from a single-level data set, and that's probably what you've always encountered so far. If you do linear regression or logistic regression, you have just a number of subjects, and every subject contributes one observation to your database, to your data set. So these are just purely cross-sectional data. These are one-level data structures, because there's no hierarchical data set below that. So that's the difficult step will be from one-level data to two-level data. Once you understand how that works, you can extend it to three-level data structures, four-level data structures, and you're almost not really restricted anymore to the number of levels that you have. Numerically, yes. If you would have a 50-level data structure, you would run into numerical problems. But from the perspective of writing down the model and understanding what these parameters mean, a 50-level data structure would not be more difficult than a two-level data structure. So the major step is from one level to two levels. And that's why we will start with that, and we will see many examples of two-level data structures, and then we will go on and continue. Terminologies that you often see is repeated measures. A typical example of these repeated measures would be with the families, but also with the patients, because within each patient, you repeatedly measure the blood pressure, for example. That's why people then refer to repeated measures data. People sometimes also refer to longitudinal data. The example with the patients or the growth curves are typical examples of longitudinal data. Longitudinal data is a very special case of these hierarchical data, in the sense that your repeated measures are always taken over time. There is like this time dimension. You don't have that with the families. I mean, if you randomly sample families and then you visit all these families and you question all the family members, there's no really ordering of these family members within the family that you're interested in. And of course, you could say, yes, I can order the family members. I can say, this family member is the youngest one, and that one is the second youngest one, and so on. You can order that. But usually, that ordering is not really of interest. If you have a truly longitudinal data structure, then you have a time dimension, and then that time dimension is of interest. Think of, for example, these growth curves of the children. There you have that time dimension. You need to know which one was the first observation, and then the second observation, and the third, and how much time was there in between. Because if you look at these growth curves, why do you do that? You want to do it because you want to study growth. You want to study how quickly these children are growing over time. So that time dimension becomes very important. Also, for the first example, with the patients, if you ask patients to come back every week for so many weeks, you don't do that to annoy these patients. You do that because you want to see how they improve, how quickly they improve. Is the improvement already present very early after the start of your treatment, or does it take some time before you start to see an improvement? You may also want to see if they have improved, does the improvement continue? Or if you stop your treatment, will then the patients get worse again afterwards? This is the kind of research questions you want to address in a study like that. So if you take these repeated measurements over time, it's like almost always because you want to study how that outcome changes over time. And you may even want to study whether that evolution over time, whether that depends on patient characteristics. For example, is there a different evolution for males than for females? Is there a different evolution for patients receiving treatment A or patients receiving treatment B? Is there a different evolution between older and younger people in your database? So there's many questions you might want to address, but they all have to do with how do people evolve over time. So in longitudinal data sets, this time dimension is crucial. And why am I emphasizing it so much? Because longitudinal data, or because of that time dimension, much more difficult to analyze. Because we will have to come up with usually a parametric model that can model that evolution over time. You will have to come up with like almost a mathematical relationship between your outcome and time. Is it linear? Is it not linear? Well, if it's not linear, what kind of evolution do we see? Is it something more logarithmic? Is it like a polynomial a model that can be used? There's many possible models that we can use, and you will see many of them in the course here. But that time dimension is always present, and we need to take it into account, and we need to correctly model that. And that's so important. For the other examples, if there's no time dimension, you don't need to model a time dimension. So that's why an example like with the habitants in the cities or the students in the schools or the family members within the families, from a mathematical or from a model perspective, these are much easier to specify, these models, because you don't have to make any assumptions about the time on one hand and your outcome on the other hand. But apart from that, the same class of models can be used, as we will see in many of our examples. So people talk about repeated measures, longitudinal data, multi-level data. You now know why that is. And they basically all refer to the same class of data structures. And yes, there are subtle differences like longitudinal data. You would never call a data set with these habitants in the cities, you would never call that a longitudinal data set. Unless if you would repeat that and you would then again question these 10 habitants a second time later on, or a third time later on. But then you would move to a 3-level data structure because you would have the cities, the habitants, measurements within the habitants over time. Then you have an additional level in your data set. But if you don't have that time dimension, it's not a longitudinal study.
The longitudinal measures have to be always about the same people? Or can you like study same thing, but with 2 weeks difference?
With different people.
With different people, yeah.
Then it's not longitudinal anymore. It would not even be a hierarchical data structure. And you need to be very careful about that. And why do you need to be very careful about it? I can show you that with a picture. Suppose I'm interested in an outcome, and let's say age. The relationship between an outcome Y could be anything and age. And okay, this would be like your scatter plot. So you have a number of observations. If I would just present you that data set and I would ask you, what do you think, what is the relation between Y and H? Well, probably you would say it's not a very strong relationship, but if you would do something like a linear regression or a correlation, you would obviously see a negative trend. And you would probably say, okay, there is a negative association between H on one hand and Y, the outcome Y on the other hand. Now, suppose that the observations that you have, and I have about 10 or 12 of these observations, suppose that these are actually longitudinal data, which you cannot see here. But suppose that if I connect the dots belonging to the same subject, that you would get the following picture. Would you still say there is a negative relationship between Y and H? Yes and no. But then we're talking about two different relationships. Cross-sectionally, and what do I mean by cross-sectionally? That's over the subject. Cross-sectionally, I still have a negative trend. But longitudinally, within the subjects, you have a positive trend. So with the example that you gave, you cannot make that distinction anymore. So you can only distinguish cross-sectional trends from longitudinal trends if you have multiple measurements per subject. And so and people make mistakes against that all the time. So they, for example, they look at different age classes between 20 and 30, 30 and 40, 40 and 50, and so on. And in each age class, they take a number of people and they measure the body mass index, for example. And the body mass index goes up, and then they say, well, if people get older, they gain more weight. That's a cross-sectional trend, what you see. All you can decide about that is that now, if you look at older people, they have a higher body mass index than if you look at younger people. But that doesn't tell you that if you would follow up these people over time, that their body mass index would increase. And errors like this are made all the time. And that's why you need to be so careful. So, and we will see examples of that later on again. But it's very important to understand that if you're interested, I'm not saying here, I'm definitely not advocating that one should always take longitudinal data or longitudinal measurements. Because the moment you take longitudinal measurements, your analysis becomes much more difficult, as we will see. But you first need to think about what research question do I want to address? And some research questions can only be addressed with longitudinal data. So if you want to study how people change over time, well, then you need to measure changes over time. And then you need to measure or need to take longitudinal measurements. And then the price to pay is that your analysis will be more complex than if you just have cross-sectional data. And this is a very simple example where you can see this. So with longitudinal data, you can distinguish the cross-sectional trend from the longitudinal trend. So if you would analyze this data set that I've shown you here, there would be two age effects in that model. A cross-sectional age effect, which would get a negative parameter, and a longitudinal age effect. And usually that longitudinal age effect, we don't call it age anymore, we call it just time, because it's the time in the study for each subject. And that would be a positive trend. And you can even have an interaction between the cross-sectional age effect and the time effect. If the younger people when they start in the study, have a different slope than the older people, then you would have an interaction between that cross-sectional and longitudinal age effect. So that's all possible, and we can test for that, and we can, if that's of interest, you can estimate that interaction, construct confidence intervals, p-values, things like that. Any other questions on this? Yes?
What is the difference between longitudinal analysis and time series analysis? If longitudinal is also interested in time.
Yes. That's actually a good question, because people misinterpret these two and mix them up. In a traditional time series is, in our terminology, a longitudinal study where you have only one subject with many, many measurements. So the traditional example of a time series is if you look at stock markets and you look every day, or what is the price of specific stocks, then you can do that for years. And you have one that you follow over time, but you have many, 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 many measurements over time. In our longitudinal data set, yes, you also have time series, but you have many, and they're very short. Because often you have only, like here, only 2 observations over time. But you have many, because you have many subjects in your data set, or many animals, or many plants, or many whatever. That's the difference. And in terms of modeling, some of the models, but we will not discuss that this year, we will discuss that next year, some of the models are very similar between these two areas. The big advantage of longitudinal data is that we still have independent pieces of information in our data set. If I have here 1, 2, 3, 4, 5, 6 multiplied by 2, 12 observations, these 12 observations are not all independent of each other. But these 2 are independent of those 2. And those 2 are again independent of those 2. Why? Because my blood pressure is not related to your blood pressure. But my blood pressure today will be related to my blood pressure tomorrow. So, because we still have independent pieces of information, we can still heavily rely on asymptotics, which is a major issue in time series, because in time series, strictly speaking, all observations are related to all other observations. And so how you do inference is completely different. Yes?
So do you have more than one longitudinal data? It is no longer longitudinal, but panel data.
But how do you define panel data?
Panel data is when you have cross-sectional and longitudinal. When you have only one animal in time, it's called longitudinal.
Mm-hmm.
When you have only one time but several animals, it's cross-sectional.
Yes.
So when you have time and different samples, it's panel data.
Yes, but then it's cross-sectional. It's at each time point you take a new panel, right? You take a new sample of individuals.
No, the same individuals measured all of time. It's called panel data.
Yeah, but that very much depends on the terminology that people use. Sometimes people refer to panel data by just taking a group of subjects randomly sampled at, let's say, month 1, and then the next month they repeat that whole experiment with new people, and they also call that panel data. But if you use the same people, then it's a longitudinal data structure. Because as long as you have the same people that you measure a second time, then it's already longitudinal. So if that's the definition of panel data that you have in mind, then under that definition, panel data and longitudinal data would be exactly the same. But that's the whole problem also, that these different terminologies have evolved for a long time independently in different areas of application. So in psychology, in social sciences, they talk more about panel data, they talk about multi-level data, but for example, in biomedical situations, they all talk about longitudinal data, repeated measures, mixed models. Then there's a whole literature on multi-level models. There's even MLWin, that's an entire package that was written to fit multi-level models, but all it does is fitting mixed models. And these things have been developed for a long time, very independently of each other, but in the end, it's all the same thing. If you go to, in psychology, people use item response theory models all the time. IRT models, I don't know if you've ever heard of that, but that's just a mixed model. And that was also developed independently of the mixed model framework. But nowadays, people realize that this is all referring to the same. All right, but we will see many examples, so if it's not clear entirely, it will become clear once we start talking about examples. Okay. The key issue, as we already indicated here, and also based on the question about the time series, is the correlation, the fact that we have correlation. So, for example, if we would have, suppose we would start an experiment and we would say, from tomorrow onwards, we agree that the first thing we all do when we wake up in the morning is we just we measure our body weight, okay? And you do that every day, for example, or every week. Then we obviously have a longitudinal data structure, we have hierarchical data, and of course, the measurements from different subjects would be independent of each other. Like what I said before, my blood pressure is not related to your blood pressure, so that's independent. But what you measure repeatedly within a particular subject is likely to be correlated. So the question now is, this correlation, should we take that into account in our analysis? Yes or no? And if the answer is yes, then of course the next question is, how? And of course you might say, of course you need to take that into account. If the correlation is there, you need to take it into account. Well, how often do we use in statistics models that are based on some assumptions that are violated, and that because of asymptotics we know that we still get results which are fine? We do that all the time. I mean, just think of a central limit theorem. You don't even have to worry about, yes, you can write down a model which is based on normality assumptions, but if your sample is sufficiently large, then you know that asymptotically your results are valid, even if the normality assumption was not satisfied. Just think of linear regression. Yes, you assume the residuals to be normally distributed, but if you have a large database and the residuals are not normally distributed, who cares? So we do that all the time, using models that do not really fit the structure of our data set, and we still get valid results. So maybe the same thing happens here. So maybe, if we are fortunate, we can use the same tools as before for cross-sectional data. We can use them in a context where we have correlated data, and we're still fine. So the first question is, should this correlation be taken into account in our analysis? If the answer would be yes, and we will have to check that, if the answer would be yes, then of course the question is, how do you do that? How do you take that correlation into account? Because think of a classical longitudinal experiment that correlation structure is not going to be a very simple one. Because if I measure my body weight today and tomorrow, I expect these two measurements to be highly correlated. But if I measure my body weight today and next month, they still will be correlated, but probably less correlated. So intuitively, you would expect that two measurements closer to each other in time are more correlated than measurements further apart from each other in time. How do you take that into account? In the model. So it's not a single correlation coefficient that you're trying to estimate here. It's like a correlation function almost. Or think of the families that we sampled, and you have then the family members within a family. You have the father and the mother, and you have the children. Would they all be equally correlated with each other? We just don't know. Maybe there's less correlation between the father and the mother than between the parents and the children, because there is a genetic link between them. So we just don't know how that correlation structure really is. So these are questions. If the answer here would be yes, then we have to address the question how, and that's not going to be a simple one. Suppose we're interested in checking whether males and females have a different body mass index. And suppose I would give you a data set with 100 body mass index measurements from 100 males and then 100 observations from 100 females. Probably the analysis that you would do is a two-sample t-test, or maybe a non-parametric version of that, but let's say a two-sample t-test. Now, suppose I would tell you that these 100 males and 100 females, that these are 100 married couples. Most likely, you would switch to a pair t-test. And the question now is, why? Why would you switch to a pair t-test? Can you no longer use an unpaired t-test? And would you get the same result? Well, I can already tell you, you will not get the same result. The pair t-test is a longitudinal technique. So if you maybe thought prior to coming to this class today that you had never used a longitudinal technique in your life yet, that's not correct. As soon as you've used the pair t-test, you've done a longitudinal analysis, because you have pairs and you have a hierarchical data structure in your data set. You have the subjects, and then you have two measurements within each subject. And then you take advantage of that data structure if you do a pair t-test. An unpaired t-test does not take advantage of that structure and does not recognize the fact that there's unique links between the 100 males and the 100 females. And because of that, you will get different results. So the conclusion is this hierarchical data structure will imply correlated data. So the only reason why we are here together now in this course is because of this correlation. If there would be no correlation, we could just happily continue to use linear regression models, analysis of variance, logistic regression, if you have survival data, Cox regression or log rank tests or whatever, because all the techniques that you have seen in other courses or in other contexts always assume that all your observations in your database are independent of each other. And it's exactly this assumption where it goes wrong if you have hierarchical data. You no longer have independent data. So going back to this question, should this correlation be accounted for, we will see yes. Because if that correlation should not be taken into account, we could just happily continue using linear regression models, logistic regression models, Poisson regression models, and all these other techniques that you have already studied in other contexts. But it's because of the correlation that we can no longer use these techniques and that we need to do something else. So an alternative term for repeated measures, longitudinal data, multi-level data could just be correlated data, because that's what we will have to deal with, the correlation in the data structure. If there would be no correlation, there would be no issue, and we would not be here in this course. So the problem is this correlation, and it's because of that I already referred to that this area is such a huge area within statistics. Because for a long time, people didn't realize that correlation in the data was really a major issue. And they just analyzed their longitudinal data sets with linear regression models or logistic regression models or whatever, depending on the nature of their outcome. But then they realized that they had to take into account the correlation, and that's where they had to start reinvent all the methodology, everything. So all the linear models no longer are valid. Linear regression, analysis of covariance, analysis of variance, it's never valid anymore. And you need to change from the linear regression model to the linear mixed models. So the term mixed, why it's called mixed, we will come to that. But mixed refers to basically the generalization of linear models to correlated data structures. Generalized linear models, such as Poisson regression, logistic regression, that now needs to be extended to correlated data, and then we talk about generalized linear mixed models. And then the same for the nonlinear regression models, they need to be extended to nonlinear mixed models. And that's why it's such a big area, because all the tools that people had developed for ages within statistics were no longer valid suddenly, the moment you move to correlated data. And then you need to use new methodology. Any questions about this? All right, then let's start to think or look for the first time at a very simple longitudinal data structure. And the most simple longitudinal data structure you can think about is a paired data set, paired observations, like what we referred to before. And an example that we have is, and by the way, I didn't mention that explicitly, but most of these data sets are also on Toledo. So if you just want to try out some of these analyses, you're free to use these data sets. They're not all on Toledo, because some of the data we can just not make public. It's not allowed. But the majority of the data sets, yes, you will find them, and that's one of them. So this is a very simple data set, 15 patients with hypertension, so high blood pressure. And these patients will be treated with a drug called captopril, and that's where the name of this data set comes from. And the blood pressure is then measured before the treatment starts and then sometime after the treatment has been given to these patients. And of course, the research question is, how does the treatment affect the blood pressure? And here you see the actual data sets. So it's a small data set, as I said before, 15 observations, 15 patients. We have then the measurement before and after the treatment, and each time we have the systolic blood pressure and the diastolic blood pressure for all these patients. And although this is a small data set, there's not much you can see by just looking at these numbers. It's much better if you just look at like summary statistics, and that's why you have here like the averages. And for example, you see that the diastolic blood pressure, that changes from 112 millimeter mercury about to 103. So there is a reduction of about 9 units. Similarly, for the systolic blood pressure, you see a reduction here. And this is how we typically will represent these data graphically. And look at these two plots, they're very similar to what you see here. So what we will always do is we will connect the observations that belong to the same subject. I mean, you could also make a scatter plot, and then you would have 15 dots here and then 15 dots there. But then you would not see which observations belong to which subject. And that's important information. Why is that important information? Well, we will come to that, but what you see here, for example, for diastolic blood pressure is for each subject a black line. The red line connects the averages. So the average blood pressure before and the average blood pressure after, so that's the 112 and the 103 here, which are connected. What do we see? We see that most of the subjects improve. Improving here means getting a lower blood pressure because they have a high blood pressure and the aim of the treatment was to lower the blood pressure. But not all of them. If you carefully look at them, there's 2 subjects here that show a small increasing trend. You would not see that if you would just plot dots. What else do we see? We see that there's a lot of variability between these subjects. Look here at the beginning, how different they are. Some are below 100, some are above, let's say, 130, about. So a lot of variability at baseline. But that variability I'm not really interested in so much. If I only would be interested in studying how the blood pressure differs between subjects at a particular point in time here, then I would not need to take these blood pressures twice. Why do you take blood pressures twice for each subject? It's because you want to study evolutions. You want to see how they evolve over time. And then we also see that next to the variability at baseline, there's also variability in how they evolve over time. Some subjects decrease much more than other subjects. And that may be very important information for a clinician. And then, of course, the next question might be, why do some subjects have a more severe decrease than other subjects? But that's additional questions. You can try to explain where does that variability come from. But we definitely see here variability between these patients. What we also see, just because we connected these dots before and after the treatment, is that not always, but for the majority of these patients, and you clearly see it here for systolic blood pressure, if a subject starts high, it tends to remain very high. If a subject starts more at the lower side, it tends to remain quite low. There's a name for that in statistics. Correlation. Right? I mean, if knowing the value here before already tells you something about you can expect after the treatment, that means that these 2 observations are related to each other and that they are correlated. So the correlation that we talked about, and that was just intuitively, by just reasoning, okay, if I measure my body weight today and tomorrow, they will be associated, these values. And if I look at my diastolic blood pressure and your diastolic blood pressure, they're probably not correlated. So we were assuming that there would be correlation in that data set, but here you can see it. You can see that there's correlation in the data. So that's why it's so important to look at these connected dots here and not just look at the scatter plots. With purely cross-sectional data, you would not be able to connect these dots because there is no connection. But if you have repeated measurements, you can connect these dots belonging to the same subject, and then suddenly you get much more information that you would ever notice otherwise. So here we can see there's a lot of variability, and we see that there's a lot of correlation. And the strange thing is that if you carefully look at this, and that might come as a surprise to many statisticians the first time you see this, why is it so obvious that a high observation here remains high and a low observation here remains low? Why is that so obvious? It's because there's so much variability. If there would be much less variability and all these curves would be almost on top of each other, you wouldn't see that. So the strange thing is that this plot seems to suggest that variability and correlation is the same. That these are two faces of the same coin. And that's important to realize, because the mixed models that we will use will never model the correlation explicitly. They will model variability. And by modeling the variability between the subjects, because that's what we're talking about, by modeling the variability between the subjects, automatically we will also have modeled the correlation in the data. And that's not the only way you can model correlation. For the people who would take the course next year, we will see other models. And you may have heard about that if you just look in the literature. People sometimes use generalized estimating equations. Basically what that is just a classical linear regression, and on top of that you put a correlation structure. Then you explicitly model the correlation. Here in mixed models, in this whole course here, we will never do that. We will model the variability, and then as a side effect, we will also take care of the correlation by modeling the variability. So that's how mixed models deal with variability. Now, before this whole course, how would you have analyzed a data set like this? Probably we already mentioned it by using a paired t-test, because you have paired observations, right? And I'm not assuming, I wouldn't dare to assume that you don't know what a paired t-test is, but let's still briefly repeat what a paired t-test is doing. What is a paired t-test doing? And if we now focus on a diastolic blood pressure, a paired t-test is calculating the difference within each pair. So you calculate the difference here, so the observation at the beginning, so before the treatment, minus the observation after the treatment, that's the change within each subject. And then you have 15 changes, and what you test is whether the average of these changes is 0. But the test you then use is a one-sample t-test applied to these changes. So we test whether the average delta is equal to 0, and then here you see the output, and this is an analysis done in Statistica, but of course all these software packages would do the same. And then you would see that the average change in blood pressure, which was about 9.2 units, is highly significant at the 5% level of significance, p-value 0.001. So that's just a very plain, simple paired t-test analysis. With that same data set, remember, the main question just prior to this section was, should we take into account the correlation? Well, we can try it out. Take that same data set and ignore the correlation. Just forget about the fact that these 15 observations before and 15 observations after treatment belong to the same subject. Act as if these would be 15 blood pressures from 15 subjects without treatment, and then 15 blood pressures from 15 subjects who received the treatment. People do experiments like that all the time. You take 30 subjects, you randomly assign them, half of them gets the treatment, other half does not get the treatment. Then this would be your database, the same observations, the same values, the same numeric values, but there's no connection anymore. So graphically, that would be the unpaired t-test situation, while this is the paired t-test situation. And then here is the result. So the variances before and afterwards are not significantly different from each other, so I can do a two-sample t-test, and the p-value would be 0.036. Strictly speaking, it's still significant on the 5% level of significance. But you clearly see that this p-value is about 36 times larger than the p-value that we obtained based on the paired t-test. Imagine what would have happened if we had decided up front to use a significance level of 0.01. Then in the paired t-test analysis, we would say highly significant. In the two-sample t-test analysis, we would say not significant at all. So this shows that ignoring the correlation is a problem. Because if you ignore the fact that there's a link between these two sets of observations, then suddenly you end up with a p-value which is way too high. So from a statistical perspective, and I think you could already have guessed this, from a statistical perspective, having 15 subjects measured twice is completely different from having 30 subjects measured once. This is a paired t-test. This is a two-sample t-test. Now, how does the paired t-test handle the correlation? It doesn't. It avoids it. It circumvents the correlation. And how does it do it? By taking differences. And the moment you take these differences, the next step is to analyze these differences, but then you have only one observation left per subject. And different subjects are independent of each other, so there is no correlation anymore. So by just taking differences within the subjects, you avoid having to deal with the correlation. Because all which is left is 15 changes belonging to 15 independent subjects. So there is no correlation anymore. So that's a very nice trick to get rid of the correlation issue. But then the question, of course, is how do you do this if you have multiple measurements per subject? Because then you cannot just take a single difference anymore and go from 4 measurements to only 1 measurement without losing information, obviously. How do you include covariate information? If you would want to know whether older patients have a different evolution than younger patients, or whether males would have a different evolution than females, and so on. Or how do you deal with multiple levels in the data structure? All questions that we need to address. But this shows here this very simple example that we now have seen for the first time is showing us that this correlation which is there cannot be ignored. So we will have to deal with the correlation, otherwise you have the risk that your p-values and all your inferences based on your analysis are just completely wrong. And so the rest of this course will be on how to deal with these correlations in more extensive situations than just the paired t-test situation. Okay, any questions about this? If not, I propose that we take a break here and we continue in about 10 to 15 minutes. Okay? All right. Let's take a look at another example. And this is a data set not from a biomedical context, but from biology. More specifically on lizards. So lizards are reptiles. We have a data set here on 102 of these lizards. And the number of dorsal shells, so these animals have, their whole body is covered with shells, and depending on the region of the body, it's a different type of shells. And here we're looking at the number of dorsal shells, which is the number of shells on the back of the animal. And the researchers were interested in knowing whether the number of dorsal shells would be gender related. So if the female animals would have more or less dorsal shells than the male animals. And I'm not a biologist, so don't ask me why they want to answer this research question, but apparently that was the research question they were interested in. And here you see the actual data. You see here the males, the average and then the standard deviation, the females, the average and the standard deviation. Here you see the two averages, so it's a little bit over 35 shells for the males, a little bit less than 35 for the females. So yes, there is a small difference, but if you then do a two-sample t-test on this, it's not significant, p-value 0.10. And that, of course, could have been the end of the story, but of course then we would not have this example here in this course. What I did not tell you yet is that these animals, some of these animals are related to each other because they have the same mother. And then immediately you get clusters. Because some of these animals are, let's say, brothers or sisters of each other, and other animals have a different mother and therefore probably are not related to the first animals. And in total, we have these 102 lizards, but they come from 29 mother animals. And the question now is this important? And of course, that might be important if you think of like a genetic effect, because these animals, they're genetically linked to that mother animal, so that creates a link between them. So the animals with the same mother are linked to each other. They have some genetic information which is in common. And maybe that creates a correlation also in the number of dorsal shells that they have. So maybe two animals from the same mother animal might have dorsal shells that are more alike than if you have animals from different mothers. And that's, of course, something that we have completely ignored in our two-sample t-test analysis, because, as you all know, a two-sample t-test just assumes all independent observations. So we expect that there might be a mother effect present, and the question then is, how do we deal with that? How do we take that into account? And just to further graphically explore this data set, I made the following plot. And what you see here on the x-axis is the number of the animal, the mother animal, and we have in total 29 mothers, but it starts here at 2 and it goes all the way to, what is that, 28, 29, 30. So that's the 29 that we have, so not all the numbers are present here. And we have 2 symbols per mother. A solid symbol, a bullet, is the average of all the, let's say, sons from that mother. So from the male animals belonging to that mother. The circle is the average of all the females belonging to that mother. So it's the daughters of that mother. And then what you see is that, well, obviously for some of the mothers, we have only one symbol. Like for mother 3 here, there's only a bullet, so that means this mother did not contribute any daughters to that database. For example, here, number 19, that there's only a circle, so there's no sons from that mother in this database. So that already shows that you have very highly unbalanced data. Also, what you don't see here is that these mothers, of course, do not all have exactly the same number of animals in that data set. So there's mothers with maybe only 1 or 2 animals, and other mothers can have more animals in that database. So it's highly unbalanced. What we also see is that there's quite some variability between these mothers. For example, look here at number 15. Then there's 2 symbols which are extremely low. It's like the 2 lowest ones of all the averages that we have observed. But then if, for example, you would look here at number 22, then this is pretty high. So here you have 2 symbols really much higher than the others. So there seems to be quite some variability between these mothers in terms of number of dorsal shells for the animals that they contribute to this database. And of course, that could be this mother effect which is taking place. So there is a lot of variability between the animals just because of the fact that they have different mothers. And that was completely ignored in our analysis. What we also see is that if you have 2 symbols, very often the boys score higher than the girls. And very often it's a big difference, what you see. Like, look here, a big difference, look here, a big difference. So we're talking about like, this is about 35, this is about 37, so that's like 2 units difference, which is much higher than what we just saw by looking at the crude averages. If the girls are higher, like for example here or here, then we're usually talking about a very small difference. So there's many questions arising here, and for sure one of the key questions is there maybe a difference between the males and the females, but maybe we just didn't detect it because there's so much variability due to the fact that these animals have different mothers. Shouldn't we take into account the variability between these mothers in our analysis? And obviously, this is a clustered data set because you have all clusters. Each cluster is like combining all the animals with the same mother. So we have 29 of these clusters in our database. So this is definitely a data structure, which is a hierarchical data structure. It's a clustered data set, like what we discussed before. It's a little bit similar to the data structure with the families and the family members. And we expect correlated observations because we've seen severe differences between these mothers, and then you expect that animals from the same mother will all be more alike than animals from different mothers because of the variability between these mothers. So the question now is, how can we correct for the differences between the mothers? Well, the most simple analysis based on methodology that we know from different courses or different contexts would be a 2-way analysis of variance. where you have two factors. You have the gender, that's the factor we're interested in, and then you have the mother effect, because that's also a factor that creates a number of groups in your database. So you have obviously two factors, and we're interested in that gender effect correcting for the mother effect. And then you use like a multiple linear regression model or a multiple analysis of variance model. And if I write that down in the typical ANOVA notation, then you have your outcome Y with three indices. I stands for the mother, so the first factor. J stands for the gender, the second factor. And then K is an index that stands for replication within each combination of I with J. So for a particular mother, for the sons, you can have multiple sons. So there might be repeated observations of sons within a particular mother. And then a classical ANOVA model would be where you have an overall mean, an intercept mu, an alpha I, that's a mother effect, a beta j, that's the gender effect, and of course the effect of interest would be the beta j, that's what we're really interested in, and then the epsilon I, j, k, these are the traditional errors that we always have in a linear model, such as an ANOVA model. So the overall mean is represented here by mu, the gender effect is beta j. Of course, we would be interested primarily in the difference between beta 2 and beta 1, because that's the difference between the males and the females. And the mother effect is then the alpha I. So that alpha I effect is there, but we're not really interested in that. We just want to correct for that variability between the mothers. Of course, this model is over-parameterized. Because it has just too many parameters. It's like in a classical ANOVA, if you have three groups and you specify it with an overall average, and then three parameters for the three groups, you have one parameter too many because you can only estimate three averages. So you need to build in additional restrictions. And what we will do is, of course, there's an infinite number of restrictions you can use, but what we will use is that the alpha I sum to 0 and that the beta j sum to 0. And because of that choice, this mu becomes the average, right? Because the average over the mothers and the average over the genders then becomes 0, and then the overall average is the mu, and then the mu becomes the overall average in outcome in this population. Keep that in mind, because you will see these restrictions coming back later on in a slightly different format. Of course, as always, we will assume the residuals to follow a normal distribution with mean 0 and with a variance sigma squared, and I use the index res referring to residual, so that we know that this is the variability of the residuals. Now, that was, what I used here was the traditional ANOVA notation. I can rewrite that model and reparameterize it slightly so that it more fits within our hierarchical dataset structure context that we're talking about. And what we then typically do is we don't use three indices, but we use an index for each level of the data structure. And that makes it much more easy to understand what we are talking about. So let me now denote by Yij the jth observation for the ith mother. So you have in your data structure, if I would write that down graphically, you have here your mothers, and that's with an index I. And then within each mother, you have the animals. So that's let's call them the children. These are the actual animals in our experiments, and these are indexed by J. And if we would later on continue with more than 2 levels, we would have, for each additional level, an additional index in our notation. And that makes it much more easy to understand the notation, and a notation that nicely reflects the structure of our database. Now, of course, if you just use a single index j here for the children within the animal, you still need to make a distinction between the male and the female animals, so I need to define a covariate for that. And I do that by x. xij will be defined as 0 if we're talking about a male. So if the jth animal belonging to the ith mother is a male, then xij would be 0. Otherwise, xij will be 1. And then the model that we had before can be rewritten in this format. So I still have the mu, I have my alpha I, my mother effect that I want to correct for, and then I have one single parameter, beta, multiplied by xij. So instead of before having 2 betas, one for the males and one for the females, I now have one beta which is directly measuring the difference between the male and the female animals. So beta is the parameter of interest. But again, I have too many parameters because there's still too many of these alphas there, and I use the restriction alpha I is equal to 0, and the residuals still follow a normal distribution as before. So far, nothing has changed to the model. It's just a slight reparameterization of the same model. So what does that model basically assume? You assume for each mother that she has her own average. So mother I star, mother I prime, they all have their own average, and then the children are distributed around the mother-specific average, and then more specifically, you have an average for the sons and an average for the daughters, and then around that average, you still have your individual observations, which are now not shown in this plot here. That's basically what the model is assuming. I can very easily fit that with just any software tool that allows me to do two-way analysis of variance, and if I would use SAS, it's like ProgGLM. So you have your outcome, the number of dorsal shells. I have the gender effect, which is a dummy covariate, 0 or 1. And then you have the mother effect here. And this is like the typical outcome or output that you would see. And then you see here, well, here your sums of squares. Look at the R squared. About 62% of the variability is explained. I mean, you rarely see that in statistics. Almost 2/3 of the variability is explained by 2 factors in that model. And of course, having seen that picture that I showed you before, where we could see all the variability between the models, we're not that surprised by this. And then here we have the individual tests for the 2 effects. The mother effect is extremely significant, not a big surprise, because you could see that almost, that there would be an important mother effect, and that's exactly why we did this analysis. But then, of course, what is much more important for us is the gender effect. P-value 0.009. And suddenly, it's significant. So with our 2-sample t-test from before, the p-value was 0.10. And we would have concluded no significant difference between the males and the females in terms of number of dorsal shells. But if I now correct for the variability between the mothers, suddenly that becomes significant. And of course, from a statistical perspective, you're not so surprised by that. Because if you really can correct by introducing an additional covariate, or here a factor, the mother effect, that explains a lot of the residual variability, you gain precision. You know that from linear regression. If you have an important very predictive covariate, you reduce your residual variability, and then all the standard errors for all the parameters become smaller. So you gain precision. Smaller p-value, smaller confidence intervals, anything like that. So we're not really surprised by this. So this looks like blue sky. This is like the ideal situation. The model does what we initially had in mind. We want to correct for the differences between the mothers. And the results really are the way we expected them to be. And that looks like the perfect solution. Well, it's not. Why not? Well, on this slide, there's one number that is a little bit problematic. And that number is this one, 28. 28 degrees of freedom. What does that mean? It means that we have been estimating in the background 28 parameters for that mother effect. Where does that 28 come from? Where it comes from the 29 mothers, each with their own effects. But since we add this restriction here, there's only 28 parameters that you need to estimate, because the last one follows from the first 28 ones, because they have to add up to 0. Why is this problematic? Well, first of all, you also know from other contexts, like linear regression, the more parameters you try to estimate, you lose efficiency. Because the information that is present in the data set is like smoothed out over all the parameters that you need to estimate. So if there's many parameters, I mean, like a linear regression model, who would ever fit a linear regression model with 30 parameters? You try to avoid that, because you then lose precision for the parameters that really are of interest to you. So you try to avoid that. Think of a situation, a clustered data set like this one, where you would not have 29 clusters, but where you would have a few thousands of clusters. Then you would estimate here thousands of parameters. Obviously, you would lose efficiency. And what is really problematic is that you're not even interested in those parameters. Why are we not interested in these 28 parameters? Because no one will wonder what is now the difference between mother 7 and mother 9. I mean, these are just arbitrary numbers. Where do these mothers come from? These animals were randomly sampled, and there happened to be that some of these animals shared the same mother. But we are not interested in these mothers. So why would you want to estimate here 28, in other contexts hundreds or thousands of parameters that no one is interested in? That effect, that mother effect, is there only to correct for the variability between these mothers, but we're not really interested in these actual mothers. Another way of formulating this is the following. If you write down a statistical model, just think of a linear regression model, a very simple linear regression model. Y is beta 0 plus beta 1, x plus your error term, epsilon. You will estimate these parameters, but the whole theory about statistics tells us that you're assuming that there is some population. You randomly sample from that population, and then based on that sample, you will estimate these population parameters, beta 0 and beta 1. And if you would repeat the experiments, so you would take a second sample, you would still be estimating the same parameters, beta 0 and beta 1, because these are population parameters. And if you would do the experiment a third time, you would again be estimating the same parameters, beta 0 and beta 1, because they're still population parameters, and you're still drawing from that same population. That's where it's going wrong in the current example. Because if I would repeat the experiment a second time, yes, I would again have maybe 102 lizards, because maybe I could restrict my sample to 102 observations. But would I have exactly the same 29 mothers? No way. Maybe I would have more mothers or less mothers. And most likely, it would be different mothers. So these alpha I parameters here, they're nothing like the betas that I wrote down here, because these are not population parameters. These are parameters that belong to that specific mother, and they do not really, or they're not parameters that characterize the general population from which you have sampled. So this gives me a little bit a strange feeling, because what we have done here, and which looked originally like doing the right thing, is like not what we typically would do in statistics. And that's why this two-way analysis of variance is not such a good idea, because it's not really fitting within the general statistical framework very well. And so where it really comes down to is the fact that we have two factors here, the mother effect and the gender effect, but they're of a completely different nature. The gender effect is a traditional effect. The beta parameter is a traditional parameter. If I would repeat my experiments, I would again be interested in estimating the difference on average between males and females. So I would again be interested in estimating the parameter beta, that same parameter beta. But for the mother effect, that's a different kind. If I repeat my experiment, I would have most likely more or less mothers, and it would be different mothers. Yes, there would again be variability between the models, but these parameters in that model would be different, because the parameters are tied to the mother. Well, because of that, we need to treat these two factors completely differently. We will call the gender effect a fixed effect. Fixed because if you repeat your experiments, it's the same parameter that you will again see in your model. And it's the same parameter that you will again be estimating, a parameter that characterizes the population. That mother effect is called a random factor, because repeating your experiment will lead to different mothers and therefore to different alphas. So these alphas, they were like generated randomly. By sampling different mothers, you sample different alphas. That's basically what it does. So we need to treat these two factors differently. So I need to find a model that can make the distinction between that gender effect, which is fixed. If I repeat my experiment, I'm still interested in the boys and the girls, and more specifically, the difference between the boys and the girls. If I repeat my experiment, I'm not interested in these particular mothers. I don't care whether I would have 29 mothers or 27 or 37. I don't care about it. I just want to correct for the fact that there's differences between these mothers. But I would never be interested in like doing a statistical test to test the difference between model 1 and model 2, or model 1 and model 14. Why would you ever be interested in that? Because they just randomly occurred. So I need a model that can make the difference between these two. Well, the way to do that is as follows. We will keep the same model as we did before, because the model made sense. But I need to add to the model the fact that these alphas here just were randomly sampled. By randomly sampling the animals, you randomly sample mothers. And if you randomly sample mothers, you randomly sample alphas. So these alphas are random. So we will treat these alphas as random values. And the moment you say random, then it means there is some distribution behind it. And you can come up with many different distributions, but the one that is the most convenient one, I'm not saying the most realistic one always, but by far the most convenient one, is again a normal distribution. Because we're talking about linear models, continuous outcomes, the error terms already are normally distributed, then it makes sense to use a normality assumption for these alphas. We will come back to that, because the normality assumption is not an assumption that is always satisfied. And then the question is, how sensitive are the results if you deviate from that normality assumption? But that's for much later in the course. So we will assume a normal distribution. The moment you say a normal distribution, as you all know, a normal distribution has two parameters, a mean and a variance. The mean, what will we put in as mean? Well, remember, before, here it is, before we use the restriction that the alphas sum to 0, such that like the mu would be the overall average. But we will keep that. So we will assume the alphas to have mean 0. And then the other parameter which is present is the variability here, which is sigma squared, now with an index mother. And that variability, so you can already see what is going on. In the first part today, I told you that we would deal with the correlation by modeling variability. Variability between the clusters. That's exactly what we're doing here. Because the clusters here are the mothers. And we're modeling the variability between the mothers. By assuming that every mother is sampled from a normal distribution, this gives that mother her own level, lower or higher, one of the two, on average 0, but if the sigma squared mother is high, there will be much variability between the mothers, between the clusters. If the sigma squared mother would be small, there would be little variability. So by doing this, the only population parameters left in this model would be the mu, the beta, the sigma squared for the mother, and of course the sigma squared for the residuals, but these are truly population parameters. If you repeat your experiments a second time, or a third time, or a fourth time, you would still be estimating the same parameters. You would get different estimates, but you're estimating the same parameters. The sigma squared mother is a parameter that characterizes this population. It measures the variability between the mothers in this population of animals for the number of dorsal shells. So this model does exactly what we had in mind. And it's because we now have a fixed effect and a random effect that we talk about a mixed effects model, or just briefly a mixed model. So a mixed model, briefly, is nothing else but a linear regression model, because that's basically what it is, where some of these parameters are fixed. The mu is fixed, the beta is fixed. So these are traditional regression parameters, population parameters. If you repeat your experiments and you would again fit the model, you would still be estimating the same parameters, so they're fixed. But the alphas here are random effects. So we have a model with some parameters fixed, some parameters random, and that's why we call it a mixed effects model, or just briefly a mixed model. Any questions about that model formulation and the interpretation and the choices made here? Okay, let's take a look at the results. Well, we can very easily fit that model in proc mixed. So mixed, well, it already refers to the name mixed models. That's a procedure designed for linear models. And basically, it looks very similar to what we had before. There's only one thing you need to always keep in mind. That is, you need to tell the software which are the fixed effects, which are the random effects in your model. The fixed effects go in the model statement, the traditional model statement. So if you would go back to where we did the two-way ANOVA, you had a model statement where you specify your outcome and then your factors, or the covariates in your model. Well, that remains the same, but now it's only the gender effect, because that's the only fixed effect left. And now I have a new statement, the random statement, where we tell SAS that we want to correct for the mother effect, but we want to treat that mother effect as a random factor. And this way you can really distinguish between the fixed effects and the random effects in the model. And let's take a look at the results. And here you see for the first time such an output, and it's the general output. And later on, when we will fit such models, we will only see parts of the output, or relevant parts of the output. But what you first see is the iteration history. And that's always important to take a look at, because we do here something like maximum likelihood estimation. You probably know, I mean, with maximum likelihood, what you basically do, and that's difficult to draw in multiple dimensions, but you have an objective function, which is your likelihood, as a function of all the parameters that you need to estimate. So what are all the parameters that we need to estimate? Mu, beta, and the two variances, sigma squared mother and sigma squared residual. And you need to find for the values for that theta that really maximizes that likelihood, or the log likelihood, the logarithm of that likelihood. So how does that proceed? It's just a numerical procedure. You start somewhere with a wild guess. For example, here, you just check what is the value for that objective function. You calculate the derivative. That all happens numerically. It recognizes that if you move in that direction, you can further increase that function, and then it makes a jump in that direction. And it repeats the whole procedure. So from here, it jumps to here. Again, it calculates the derivative, and it makes jumps until it recognizes that the first order derivative is about 0, and that's the end of the procedure. And that's what you see there in the top table on this slide, the iteration history. So it's that history by itself is not so important, but what is important is that you get the message convergence criteria met. So that it stops, and that it stops because the first order derivative is basically 0. Because if you fit difficult models, complex models with many parameters, you may end up with non-convergence, especially the moment we move away from the linear models, as I indicated before, that you have all these special approximations, then you sometimes get non-convergence. So it's important that you have the message that convergence criteria were met. And then here we have two tables. A table with the fixed effects, so that's the mu and the beta. The mu is estimated as 35, and the beta effect was estimated as minus 0.82. So you remember the covariate gender, the x was 1 for a female and 0 for a male. So on average is the difference between males and females estimated as 0.82, where the females score lower on average than the males. But what we see is that it's significant. So, and it gives me a p-value very close to what we got with the two-way analysis of variance. So you do the correction for the variability between the mothers, but you don't have to estimate all those parameters for all those mothers. Here we see the covariance parameter estimates, and these are these two variances. The variance between the mothers is 1.78 about, so that's the variability between the mothers. And then the residual variance, that's if you take a mother and you take a gender, how much variability is then between the boys belonging to that mother or between the girls belonging to that mother? Well, the variability, the residual variability is 2.25. And then below here, you always still have an overview table with tests for the fixed effects, but of course here that's the same p-value that we obtain because it's just that same gender effect. So what did we see? We have an iterative procedure to estimate, and again, I'm not going to discuss that in detail. Next year that will be discussed. That's for this course not so important. We see a significant difference between males and females. With the original t-test, that was not significant. So taking into account the variability between the mothers gives me a significant difference between the males and the females. So I can now really detect that there is a difference. The difference is estimated as 0.83 about, and then these two variances are estimated as 1.78 and 2.25. Any questions about this? Yes?
Using this random effects model, the effect of sex is the same, not using the same model, the traditional model.
That's something that we will often see coming back later on. So what you're referring to is this here, the estimate, that whether you correct or not, you basically get the same result. And basically what you're saying, if I reformulate what you're saying is, whether I add here this random effect or not, you basically get the same estimates for the fixed effects. And that's something that we will see over and over again. Does that mean that we can just ignore the alphas? No, because the alphas will not change my estimates here very much, but it will change the standard errors, and therefore my p-values and confidence intervals. And they will become much more efficient because I now explain part of the variability, a big chunk of the variability in the data by taking into account the fact that there's so much variability between the mothers, which is now explicitly modeled. Like in the what?
Comparing with the case that you put 28 parameters.
Oh, also there, in terms of estimates here, that will not so much make a big difference. The most problematic thing is if you have really a very large number of clusters where you would have hundreds or maybe thousands of parameters to estimate, which do not, or of no interest at all. That's what we absolutely want to avoid. And now, and what is much more meaningful in practice is to know, yes or no, is there a lot of variability between the mothers? And we now have directly an estimate for that. So that's the sigma squared between the mothers. So here, that's the 1.78. That's of importance. And the other thing, which we have not discussed yet, is analysis of variance with the two factors assumes all your observations to be independent. Because that's just a linear model. And of course, you now might wonder, how does that now change? By just making these alphas here random, do we then no longer assume these observations to be independent of each other? No, as we will see now in the next section. So that's the additional big advantage of making these alphas random, that we suddenly will no longer assume the observations to be independent of each other.
If the random factor explains the variability, then if we know more random factor like further, like temperature, like sunlight, should we all add up in the model?
If there's more, well, that's a good question, actually. If there's more factors like mother effects that you know to be present, of course they need to be present and you need to have measured them, then yes, you can take that into account in a similar way. And you can have multiple random effects. Like at the end of this chapter, we will come back to that because you refer to the mothers, to the fathers, but that's a really good one, because it turns out that indeed we ignored here the father effect. And what happens is that these animals are very naughty animals. Some of the animals have the same mother but a different father. Some of the animals have the same father but a different mother. And some of the animals have the same mother and the same father, and then a fourth class of animals have completely different fathers and mothers. And you can imagine what's happening. You then have variability between the mothers that you can take into account, variability between the fathers. But if you think back of the correlation, which we have not discussed yet, but I already hinted on that this model does take into account the correlation, you might expect that if two animals share the two parents, that they will be even more correlated than if they only share one of the two parents. So by taking into account these additional factors, we will better model the whole association structure in our data set. But it's now still too early to see that. We need to do some additional calculations to see that. So let's take a look at that. And this is what we call the hierarchical versus the marginal model. Because the model that we have written down here, so that was this model with the normality assumption for the alphas and the normality assumption for the epsilons, this model can be rewritten as follows. You can say conditionally on alpha. What is the model for y? Well, the model for y is a normal distribution with mean mu plus alpha I plus beta xij, because I condition on the alpha. And then the variability comes from the residuals. So that's the residual variability. And then on top of that, you assume the alphas to follow a normal distribution. I call this the hierarchical model because this reflects the hierarchical data structure. Conditional on alpha means pick one of the mothers. The data that you then have, that's represented as, well, these are the data belonging to that one of that specific mother. That's the first model here. So the normality assumption conditional on that particular mother, that's represented here as the variability between the children all belonging to the same mother. And if you go one level up, then you say, okay, now we have different mothers, but that's the second line here. These mothers come from a normal distribution, and all these mothers have their own parameter alpha I. So you have to imagine this as you randomly sample mothers, and each mother has her own alpha I in the pocket. So sampling mothers is the same as sampling alphas from a population of parameters. So we call this the hierarchical model, which really reflects the hierarchical data structure. What is now the marginal model? Well, it's the model that explains what is the marginal distribution for y, not the conditional one anymore. So you integrate out the alphas, basically. So technically, if you really would like to do that mathematically, but of course we're not going to do that because there's a much easier solution, the marginal distribution of y is the conditional distribution of y, conditional on the alpha I, where you integrate out all the alpha i's over the alpha I distribution. This is a normal distribution, that's the top line. That's a normal density, that's the second line. You multiply them, you integrate that over alpha, and then the alphas disappear out of that model, and you have the marginal density for your y's. Now, you can do that analytically, and you can try that at home if you like that. It's not that difficult to do. It's just a matter of reshuffling a little bit the exponential terms in these densities here. But you can do it much easier from just looking here at this expression. The alpha is normal. The epsilon is normal. So y needs to be normal. Right? What will be the mean of that normal distribution? Well, the alphas have mean 0. The epsilons have mean 0. So the mean of that normal distribution will be mu plus beta x. So the only thing we still need to calculate is like the variance. And we will always assume, I did not explicitly mention that yet, that the alphas and the epsilons are independent of each other. So that's what you see here. Well, if the variance of y needs to be calculated, then it's the variance of alpha plus epsilon, because the mu and the beta do not contribute to the variance because they're fixed. So the variance of alpha plus epsilon, if they're independent, it's the variance of alpha plus the variance of epsilon. So it's the sum of these two variances. And that's what we see here. So the marginal density of the marginal distribution for y will be a normal distribution with mean the fixed effects. So take your model, take your mixed model, and remove everything which is random. The fixed part, that's your mean structure. So that's the same like in a traditional linear regression model. So the average, and that's the nice thing about these mixed models, the average, which is often of primary interest, the average trend in a population, or the average effect in a population, is directly seen by just looking at the fixed effects. If I want to know what is the average for the males, it's mu, because the x is then 0. If I want to know what is the average for the females, it's mu plus beta, because then x is equal to 1. The variance is the calculation I just explained, so it's the sum of the two variances. What about the covariance or the correlation? Because that's what we're interested in. I already said that we need to take into account that correlation. Well, how is that done here? Well, if we take two observations from different mothers, so you take two animals and they don't have the same mother, then let's say the first child has mother I, the second animal has mother I star, then this would be the expression for the outcome for the first animal. That would be the expression for the second animal. You can calculate that covariance by just removing all the fixed effects because they don't contribute to the calculation of a covariance. You only have the random terms left. A covariance of a sum is the sum of the covariances. And then we have the covariance between two of these alphas, but of course, two different animals, two different mothers are independent. So that first term would be 0. The alpha and the epsilon, they're independent. That's an assumption we've made. The same here, epsilon and alpha are independent. The residuals are independent, so the covariance is 0. So take two animals with a different mother, and they will be independent. That's what you would expect. That's what I said before. My blood pressure is not related to your blood pressure because we have nothing in common, I believe. But if you take two animals with the same mother, then this cannot be repeated anymore. Take two animals with the same mother, animal I, then they, in their model, they would have the alpha I in common. And then everything continues the same as on the previous page, except that you would have here the covariance of alpha I with alpha I. And what is that? It's the variance of alpha I, so it's the sigma squared of the mothers. And this is what I told you before, that we will model variability, and implicitly we have taken care of the correlation. Because this model implicitly assumes that two observations from the same mother, so if you take two animals and they have the same mother, that these two animals would no longer be independent of each other, because the covariance would be alpha I. And what we also see is something we have had observed before when we looked at this plot with the Captopril data sets. If you have more variability, there's more correlation. If the variability between the clusters, between the mothers is higher, you will have more correlation. If the variability between the mothers would turn out to be very, very small or eventually 0, then there's no correlation left. And that's exactly what we observed when we looked at these individual profiles. When I said, if all these profiles would be on top of each other, there would be no correlation left anymore. But that's what you see here, but now mathematically speaking. And now, of course, if you have the variance and you have the covariance, you can calculate the correlation. And that correlation is the covariance divided by the variance, or the multiplication of the two standard deviations, and that's 0.44. So based on this model, based on this analysis, we can estimate that the correlation in number of dorsal shells of two lizards sharing the same mother is about 0.44. But what you see is that this correlation really depends on the variability between your clusters. More correlation between the clusters, more variability between the clusters, higher correlation within the clusters. Less variability between the clusters, smaller correlation within the clusters. So correlation will be low in cases with little between cluster variability relative to the between cluster variability relative to the within cluster variability. And that's what you expect. If there's no variability between these mothers anymore, then all these mothers would be at the same level, and then there's no difference anymore. And whether you then take two animals from the same mother or from different mothers, there's no distinction anymore between them. Any questions about this? All right, just to conclude, let's go back to our Captopril data set, because we've then seen, when we analyzed the Captopril, that this paired t-test was like circumventing the correlation issue by taking these differences within subjects, within pairs. But could we also use a mixed model to do that? The answer is yes. And you will get the same results. So a paired t-test is basically doing the same thing as a mixed model, but in the most simple situation where you have only 2 measurements per subject. So let's go back to our captopril data set, and let me focus again on the diastolic blood pressure. This is the result from the paired t-test situation. And if we now would turn it into a mixed model formulation, what would we have to do? Well, we're of course interested in that difference between before and after treatment. That's what we definitely want to know. So that's going to be like a fixed effect. What would be the random effect here? That random effect will be the cluster, the patients. So every patient has its own level. So we need a random effect to represent that. So let's denote by Yij the jth measurement for the ith patient. So the first index is always the top level in the data structure. The second index is the level below. So the I is here. Before it was the mothers, now it's the patients. And the J is then the measurements within the patient. And the J is 1 or 2, because we have only 2 measurements per subject. And of course, we need to make sure that we can distinguish the measurement before the treatment from the measurement after the treatment. So similar to before, we had males and females. Now we denote it by T, Tj, which is 0 or 1. And why T? Because it's really a time effect. Before we used X for the gender, the difference between the 2 genders, but T now, of course, you can use X as notation, but it's really a time. It's before the treatment, after the treatment. So let's use T, and already get familiar with the notation where we would go into longitudinal data structures. So T is 0 before the treatment and 1 after the treatment. And then a mixed model would then be of the following form. So you have an overall intercept, you have your time effect, and that time effect is, of course, of key interest because that tells you what is the difference on average in diastolic blood pressure before versus after the treatment. And then the mu would be your overall intercept, and that's going to be the average value in diastolic blood pressure before the treatment, if time is 0. And after the treatment, the average would be mu plus beta. And so the difference between the two, that's beta. And then you have your alpha I here, which is the subject effect, the variability between the patients. And now note what happens if you did, when we did the paired t-test, what we basically calculated was yi1 minus yi2. That was this delta I. If you apply that with this expression, then you have mu plus alpha I plus the first observation has t equal to 0, so that disappears. So plus epsilon I1 minus, so that's the first observation, mu plus alpha I plus beta, because for the second observation, the time is then 1, plus epsilon I2, and if you work this out, then this cancels out with this, and here you see the alphas disappear. That's where you avoid the correlation. You remove the variability between the clusters. That's why a paired t-test is more powerful. It's a source of variability that you completely remove from the data. The variability between the subjects is completely taken out. And the only thing which is left is beta plus, and then you have epsilon I1 minus epsilon I2, and these are the traditional error terms in a one-sample t-test. So that's how you see that this is how the pair t-test avoids this whole correlation structure. And it removes the random effect, basically. If we now do that in SAS, so you would have your time effect, which is 0 or 1, the random subject effect, so the time effect is a fixed effect, the subject effect is a random effect. You have the 15 subjects here listed up. The variability between the subjects is 96, a huge variability between the subjects, and we had seen that just by looking at that plot. The variability within the subjects, the residual variability is 37, so that's much smaller than the variability between, so you can already guess what's going to happen with the correlation. The correlation will be huge, because a lot of variability between the subjects, little variability within the subjects, and then the correlation will be very large. Solution for the fixed effects is then given here, and you see your time effect, that's your difference between the measurements before and after, on average, 9.27, the same as what we had before with the pair t-test. What it should be, because it's that parameter, beta, and if you do if you do your pair t-test, the average is that same parameter, because this has average 0. You will notice that if you look here, the test statistic, the F-test statistic, 17.36, it's exactly the square of the t-statistic from your pair t-test. So you take your pair t-test statistic. What is that? It's your estimate divided by the standard deviation over the square root of the n, and the n is then 15, because you have only 15 differences anymore. Well, that's exactly the same on 14 degrees of freedom, and that's exactly what we see here, 14 degrees of freedom. So it's exactly the same. A pair t-test is nothing else but a mixed model, but then in the very specific situation where you have only 2 observations per cluster. Let's also take a look at the hierarchical versus the marginal model, and you will see that kind of calculations several times also in the future, but it's always the same kind of calculation that you need to repeat as what we did a few slides ago. So this is the hierarchical model. What is the implied marginal model? It's always a normal one, because everything is normally distributed in these models. What is the mean? Only look at the fixed effects. What are the fixed effects? Mu plus beta times time, t. What is the variance? The variance is the sum of the two variances that we have estimated. So it's the variability between the subjects and the residual variability, which makes sense, of course. What is the total variability in your outcome? It's the variability between the subjects plus the variability within the subjects. And that's the total variability. And that's what you see also in this expression. Obviously, observations from 2 different subjects will be independent, because they have nothing in common, no random terms in common which are correlated. But if you take the 2 observations from a single subject, they share that random subject effect. And if you share something which is random between 2 observations, that creates an association. So observations from the same patient will be correlated. It's the same expression again as what we observed before. And then you can do the calculation. So the total variability is 133. The within subject correlation is 0.72. So huge correlation. And of course, we're not surprised by that. So it's all the same as with the pair t-test. There's one subtle, small, tiny, little difference. And that is, if you would say, okay, I have paired observations, and now I'm interested in calculating the correlation between them, what would you typically do? You would just calculate the correlation between your observations before and the observations afterwards. the Pearson correlation coefficient. That's not going to be the 0.72. If you do the calculation, you will get as Pearson correlation coefficient 0.73. It's not much different, but it's slightly different. Where does that come from? Well, there's one difference between the model that we use here and what you do in the Pearson correlation coefficient. When you calculate the correlation between two variables, you don't assume that these two variables have the same variance. You can calculate the correlation between height and length. Of course, you would not make the assumption that height has the same variance as the length of all the people. So they have a Pearson correlation coefficient allows the two variables to have a different standard deviation. Our model here does not allow that, because we have calculated here that the variance of y is the sum of these two variances. And that's the same for the first measurement as for the second measurement. So our model that we now have introduced implicitly assumes that the variability for the first measurement is the same as the variability for the second measurement. So that's the only small difference between this paired, well, between a traditional correlation analysis and a mixed model. So, and if you look at the summary statistics, then you will see that indeed there's a small difference in standard deviation between your measurements before and after, and that's reflected in a slightly different estimate for the correlation coefficient, because our model restricts these two variances to be the same, while a Pearson correlation analysis does not make that assumption. But that's the only difference. But so, in basically what it says is the correlation within a cluster, within a patient, is this expression. So it means if there's a lot of variability between the subjects, little variability within the subjects, you will have strong correlation. If the reverse happens, you will have little correlation. And graphically, that's what this means. A lot of variability between the subjects and little variability within the subjects, so they all change a little bit, but not much, then you typically have that a subject starting high tends to remain high, a subject starting low tends to remain low, and that means a lot of correlation. But if the reverse happens, and that can be that there's little variability between, or that there's certainly much more variability within, that all these curves start to go in different directions, then you have more crossing curves like what you see here, and then you have much weaker correlation. So intuitively, I think it all makes sense. But the key thing here is that we need to understand that with mixed models, we will take into account the correlation, not by modeling the correlation, but by modeling variability between the clusters. And then as a consequence, as a result, we also implicitly take into account the fact that not all observations are independent of each other. That's what's happening. So, to conclude here, obviously, the most simple example of a mixed model is a paired t-test. But that's only for a situation where you have a longitudinal study or where you have a repeated measure study or cluster data with only 2 observations per subject, per cluster. That paired t-test circumvents the correlation by taking these differences. In the mixed model, you explicitly model that variability between the clusters by these random effects. A question now, well, there's many questions that come up. What if we have more than 2 observations per cluster? Well, the mixed model can handle that. The paired t-test cannot handle that. Suppose you would have paired observations, but for some patients, one of the two measurements is missing. You cannot do a paired t-test, but you can still do a mixed model. A mixed model is still possible if for some of your clusters you have only one observation. We've not really explicitly discussed that yet, but if you go back to the lizard data set, there already we said not all clusters need to be of the same size. You can have large clusters, you can have small clusters. How small can it get? As small as one. And then you still can take these into account in your analysis. While for a paired t-test, you would lose them. What if you have more than other covariates? Like you would want to study now, how do different groups of subjects evolve? Males, have they a different evolution than females? Or different treatments, do they have different evolutions? And things like that. A paired t-test cannot address that. Mixed models, yes. All we need to do is put in additional covariates. We will do that next week. And then models with multiple random effects. So that goes back to the question from before. What would you do if you also want to take into account the fathers? Well, we now had the random effect for the mothers, also put in a random effect for the fathers. And if you would then do the whole calculation with the correlations, then two animals who have completely separate parents would be independent. But if you have two animals with the same father, but a different mother, they would share the father effect. And that would create some correlation. If they would not only share the father, but also the mother, they would share the father effect and the mother effect. So they would have more in common, and that would lead to a higher correlation. And that's what you would intuitively expect. The more you have in common, the higher the correlation should be. The less you have in common, the smaller the correlation should be. And if there's nothing in common, the correlation is zero. So it's intuitively quite appealing to use this kind of models, but how we will do that is something that we will discuss later on. Any questions? Remaining questions? Or new ones? All right. Well, if not, then I think we can conclude here for today, and we will continue with this next week. See you then.